Okay, with this question we're going to we have a particle that's projected from a point A on the horizontal plane, with the speed u at an angle of elevation alpha and moves freely under gravity. And for the first part we need to show that that P hits the ground at a distance or at a point P, and we've got to find the distance AB. So basically we've got a situation like this, haven't we? We've got a projectile, there's A, there's B, it's been it has initial velocity u, it makes an angle alpha with the horizontal. Okay, now we know that gravity is going to, acceleration due to gravity is going to be downwards, so we've got gravity acting downwards, and as usual we'll need to consider the two components, the horizontal and the vertical components of our velocity here. So if we resolve these into its horizontal component ux and its vertical component uy, where we've got ux will equal u cos alpha and uy will be u sine alpha. Okay, so we first of all we'll just consider the horizontal motion where there's no acceleration in the horizontal direction. So so horizontal motion where acceleration equals 0. Well, now I can find an expression for the distance using the Suvat equation, s equals ut plus a half at squared, where u is going to be the velocity. I should actually write a little x there. Ux is the velocity in the horizontal direction. Okay, so I've got uxt plus a half at squared. Now a is 0, so therefore this is just equal to ux times t. So so from this horizontal consideration we've got the fact that the distance s, which is the same as the distance AB, is going to be ux times t, and we said that ux is u cos alpha, so it's going to be u cos alpha times t, and I'm going to call that equation 1 because I'm going to use that with these sort of problems. You very often have to come back to, or we're going to use this equation later on in the problem. So carrying on now, we're going to look at the vertical motion. Now with the vertical motion a is not equal to 0, and so I've got to consider the acceleration, and the direction is going to be important. So I'm going to choose, because I'm starting off with an initial velocity in the vertical direction pointing upwards, I'm going to take upwards as positive. Okay, in my equations. So once again, using the Suvat equation, we've got s equals uy t plus a half at squared, and because a is not equal to 0 we can't just cancel it out like we did in the last example. So what do? Well, we've got to remember that that now the displacement s, in the time it takes for the particle to move from A to B, the displacement in the vertical direction is 0 because you've gone up, you've gone in the vertical direction up to the maximum height, and then you come back down to where you started from. So as far as your distance above the horizontal is concerned, it's 0. So S is going to be 0. Uy is going to be U sine alpha. And the acceleration due to gravity pointing downwards against in the negative direction, so the acceleration is going to be minus g. Now when I plug those into this equation, we're going to get 0. So we're going to now have 0 equals u sine alpha t, u sine alpha t, minus, because g is negative, minus a half g t squared. Now if I take out, there's a common factor of t here on the right hand side, so I'm going to take out t as a common factor, so 0 equals t into u sine alpha minus a half gt, taking the factor out of 2 out. Because it's equal to 0, I know that either t equals 0, which is obviously the wrong, not t equals 0 is going to be wrong. So the only alternative solution to this equation is going to be that u sine alpha minus half gt equals 0. So u sine alpha minus a half gt equals 0. And taking the half gt over the other side and rearranging this, we get that t is 2u sine alpha over g. Okay, and I'm going to call that equation 2. Right, now finally we want an expression, as we saw, for AB. So we want what AB equals. So I'm going to use this value of t that I've discovered from the vertical motion, and I'm going to plug it into the equation 1. So substitute equation 2 into equation 1. We get that AB equals u cos alpha times, I'm just going to move this up in case it's out of vision, u cos alpha times 2u sine alpha over g, which is 2, bringing the 2u over here, we get 2u squared sine alpha cos alpha over g, and that gives us the distance AB. In fact, it gives us the range of the projection of this particle. Okay, so that's that covers part A, and now I'm going to look at part B. Okay, so part B is to find, so this is 3B, find the initial speed of the javelin. Oh yeah, it then says that an athlete throws a javelin which lands a horizontal distance of 61.25 metres from where it is thrown. The initial angle of projection is 45 degrees. The javelin is initially modelled as a particle projected from the ground level and moving freely under gravity. So basically we're going to use that formula that we've just got. So we're going to use the fact that AB is 2u squared sine alpha cosine alpha over g. And we're going to plug in the fact that for this Javelin we've got AB equals 61.25, alpha equals 45 degrees, and G is 9.8 meters per second squared. Okay, and now with those, now the thing that you want to remember here is that sine alpha and cos alpha, when alpha is 45 degrees, they are the same value. Sine 45 is the same value as cos 45, and it's equal to 1 over root 2 in surd form. So it's so instead of having to look these up on the calculator, I know 1 over root 2 times 1 over root 2 is a half, and 2 times a half becomes 1. So when I plug in alpha equals 45 for this, we're going to get the AB, so 61.25 is going to be, well, I'll put it in 2 times u squared times 1 over root 2 times 1 over root 2 all over 9.81, 9.8. Okay, so all of this cancels, those cancel out, and when I rearrange this I get that u squared is 9.8 times 61.25. And when you solve this for u, you get 24.5. Okay, 24.5 meters per second squared. So meters per second. Okay, so that covers part B. Now part C, I think that's find in seconds to 1 decimal place the time of flight of the Javelin. Okay, well for this I'm going to go back and to when we looked at the vertical motion. If you recall, when we looked at the vertical motion before, you remember that when we looked at the vertical motion we came up with an equation 2 which said that the time it took, the time of flight, was 2u sine alpha over g. So I'm going to use equation, so from equation 2, the time of the flight of the Javelin is going to be equal to 2u sine alpha over g. So all I've got to do for this is plug in my values that I've got for u and alpha. So I've got 2 times 24.5 times 1 over root 2 divided by 9.8. And when you work that out and write your answer down to 1 decimal place, you get you get t equal to 3.5 seconds. Okay, so that covers us for part C. Now it talks now about a refinement that's been made to the Javelin. I'm just going to move my paper upwards slightly so it's so we can see this. Now for the for part D, we realise that the Javelin is not thrown from the ground exactly, it's thrown from a position above the ground. So if this is our original projectile, if that's originally our projectile, when the Javelin was modelled as a particle leaving from the ground, the Javelin is now going to be modelled as a particle which is projected above the ground. Okay, so a certain distance above the ground. Right, now if you now, in both cases gravity is exactly the same and acts downwards. So and as you know, a projectile is a symmetric equation. It's a symmetric function. It's a quadratic equation. And so if we project it at a certain height h above the ground, the path that the particle takes is going to be exactly the same as the path of the other particle, except it's going to be that height basically when it's going to be exactly the same parabolic shape, except it's shifted up by a distance h in the y direction. Okay, so clearly you can see that if the javelin is actually modelled or is thrown from a slightly higher elevation, then it's going to land. It's not going to land at B. It's going to land at a new position, B dash, which is greater than B. Okay, so now it says in the question that a refinement of the model is to take into account the javelin being projected from a point above the ground rather than from the ground. The initial angle of projection is the same. Okay, so they're both projected at an angle of 45 degrees or alpha. State with a brief reason whether your answer to part B would be increased or decreased. Well, part B was said the distance covered by the javelin would be part B. It also says when it's modelled that the initial angle of projection and the horizontal distance travelled are unaltered. Okay, so in order to be unaltered, this javelin must be therefore projected at a slightly smaller velocity, because this is if it's projected at the same velocity as before. It will take the dotted path and it would travel further. So in order for it to travel a distance which is less than b dashed, it will need to project it with a smaller velocity, so it would follow a path which goes like that. So the answer to D is it's decreased. The velocity, the initial velocity, must be decreased in order for it to satisfy those conditions. Okay, hope that's helped.